Okay, we're ready to go here. Today, we're going to start studying interference, which is out of chapter 35 in the book. And today we'll be looking at sections probably 35.1 and 35.2, possibly into 35.3. I'll try to make some headway on that anyway. And interference is when we start considering the wave nature of light. And in this particular section, we'll be looking at how light from two different sources can interfere. Light is a wave interference is a wave effect. And back when we studied waves, we had things like maybe y of x and p is going to equal some maximum amplitude times maybe a cosine of kx minus omega t or something like that. We might also have a phase added onto there, things like that. Well, in the case of light, there isn't a physical thing that's moving. What the light wave is composed of is electric and magnetic fields. So those are things we have not studied yet. However, they can be described with the same magnetic or mathematics that we happen to have up here. And so we'll be doing that. In particular, we'll be just thinking of the electric fields. Turns out electricity and magnetism and the electromagnetic waves are tightly enough linked so that if you describe, say, the electric field accurately enough, you can also determine the magnetic field from it. And so we're not actually going to deal with what an electric field is. That'll be the first week or two of next quarter. But for now, we can just use some of the letters. And so we might think of an E of R and T as the magnitude of an electric field. And it might look like, say, some maximum amount. That would be the amplitude of the wave. And then a sine of kr minus omega t, where using a letter R, it can be a particular distance away from, say, the source of the waves, and that can be in any direction. And then the omega t part is the kind of time variation of it. Then omega would equal 2 pi times the frequency, just like it did back when we studied other waves, or 2 pi divided by the period. We're not going to deal much with the frequency or the period of the light waves. Turns out they're really high, like 10 to the 14th or 10 to the 15th hertz, things like that for visible light. But we are going to deal with the wavelength quite a bit. And K is going to be like it was back when we studied other waves, where it's 2 pi divided by the wavelength. And then R is just some point in space far away from where you happen to be. Now, if we've got two sources of waves, we might have an E1, say, that looks like maybe some E cosine of omega t plus phi. We're going to pick some point in space where that's what it'll happen to have. And the phi is going to be a phase difference that can arise because of maybe both waves started out from the same point in space, or at some point in space they were identical, but then because of their traveling different distances, different values of r, phi can arise because of that. And then maybe E2 could be some other wave, and it'll be just plain E cosine of omega t. So at this point in space, we might measure it like that. And then when we add these two things together, we can get an interference effect. And so that's what's going to be causing this. Now, have interference occurring because of a path length difference. We'll suppose that the two waves start out nicely behaved, and in fact, we would call them coherent waves. And so when we study these interference effects, we have to have them be coherent. That means at a particular point in space, they have to maintain some constant phase with respect to each other. So at particular points, they have to be of an identical wavelength. If they aren't, at least in vacuum, they have to be identical wavelengths. One of the examples we may do today has waves traveling through from two sources actually, but they're traveling through, one of them travels through one medium and one of them travels through a different medium, and that ends up giving them different wavelengths in those media, but then they're going to be recombined in, say, air or a vacuum. But anyway, they have to be identical wavelengths. If they aren't identical wavelengths, they're also not identical frequencies. And that phase relationship up here isn't going to apply. It's just going to be changing all the time. And then the superposition principle must apply. The total electric or magnetic field is the sum of the individual electric and magnetic fields. So for this thing I was describing over here, at some point in space, you'd be interested in E1 plus E2. That'll be our E total. And it's just going to be the sum of these two things. E cosine of omega t plus phi and plus just E cosine of omega t. And we'll do little trigonometric things and graphing techniques to show how we might be able to add these two things together. Something we'll be interested in is the intensity of light at some point in space. And it turns out that the intensity of the light is going to be, let's see, I'm not sure which letter I want to use for this, but it'll be proportional to the square of the electric field. And in fact, the proportionality constants that show up in there look a little bit scary, but I'll just bunch them together in parentheses here. Let's see. I think I caught them all there. Yeah. That's the intensity of the wave, and that's how much power per unit area is delivered by it. The E here is the strength of the electric field. We're not going to worry too much about these things. Later or next quarter, we'll learn what an electric field is. But then this is just a proportionality constant. It's kind of like the capital G gravitational constant. And this is the speed of the wave. And so the intensity is proportional. All of this stuff can just be grouped together as a single constant. And that's what the intensity will look like. And when we figure out the intensity of two waves, turns out we'll end up using the law of cosines, and that deals with the square of some of these things. So we'll mess with that, but not worry about it too much. Now, something else that'll show up, much of the time, a phase difference will be proportional to a path length difference. That's what puts things out of whack. And we'll use the Greek letter delta, which I'm not very good at drawing. It sort of looks like that, although it's not flat there. Anyway, that's just a lowercase delta. And that's going to equal what we'll use to stand for a path length difference. What we'll be interested in is how many wavelengths fit into that path length difference. And so delta divided by lambda will equal the number of waves in that path length difference. In the path difference. And this is all really abstract so far. That's okay. A lot of this is going to be abstract. And if I multiply that by 2 pi, for every wave of path difference, the phase difference will end up being 2 pi. And so delta divided by lambda times 2 pi is the phase difference. And that's what this is. So we can get constructive interference if the phase difference is equal to 0. Then you're just adding these two things together. Or if the phase difference happens to be 2 pi, because adding 2 pi onto something, one of these things, is just displacing the same wave sideways by 2 pi, and you don't get things being out of whack. Or 4 pi works, things like that. So we'll be interested in when we can have constructive interference and when we have destructive interference. So for constructive interference, our phase difference now, constructive interference means the maxima of the two waves will add together. And so you get something nice and big in that case. And for that, we'll have the phase difference between the two waves, which sometimes we just write as just plain old phi, but it'll be 2m times pi, where m can equal 0, 1, 2, dot, dot, dot. So that's something that we'll have in that case. And again, the delta that shows up in that case, well, let's see. If delta over lambda times 2 pi is going to equal 2m pi, well, we can take a 2 pi out of each one, and it turns out that if the path length difference, that's what delta is equal to an integer number of wavelengths, then we get constructive interference. You get the waves matching up really nicely and adding together constructively. Destructive interference, however, and these aren't the only things that can occur. You can have everything between partial constructive interference or partial destructive interference, but that can be going on. So destructive interference, in that case, the phase difference is going to equal odd numbers of pi. And that's going to be kind of weird. Well, how do I get odd numbers of pi? Well, that would be pi, 3 pi, 5 pi, and so forth. Well, we'd have, let's see, how could we write that all together? We can say that if I take a 2 and multiply it by m plus a half, and in this case, m can again equal, whoops, and then I need to multiply it by pi. Okay, and if m is equal to 0, 1, 2, dot, dot, dot. By the way, I could have plus or minus 1, plus or minus 2, and all kinds of stuff. But if m is equal to 0, 2 times a half is 1, and I'd get pi. If m is 1, then I'd have 2 times 1.5, which is 3. If m is 2, I'd have 2 times 2.5, which is 5, and so forth. So that would produce that. Okay, well, where did that delta phi come from? It came from a path length difference, and delta phi is equal to the path length difference, delta, divided by lambda, times 2 pi. And in this case, it would be 2 times m plus a half times pi. Well, I've got a 2 pi here and I've got a 2 pi there. What it means is that the path length difference itself, if you do a little bit of algebra on here, it will equal m plus a half times lambda. And again, m is 0, 1, 2. You get destructive interference if the path length difference is half a wavelength, 3/2 of a wavelength, 5/2 of a wavelength. And that's what can cause destructive interference. Now, the first kind of interference we're going to be interested in is what's called two-slit interference. And it happens when, I'll draw some kind of a thing here. Let's see. Okay, so we'll imagine that we've got something that looks like this. And we're going to be looking down on this from above. And light waves come along here. So they're all traveling in this direction. This could be the wavelength. The separation between peaks of the wave would be the wavelength lambda. They come here, and the light from these two slits here, that's what they if you look at this face on, you'd see some, whoops, I don't want to draw it up there, too late. Anyway, you'd see something that just looks like something that maybe has two openings on it, and those are the two slits that the light can go through. And we'll show this stuff in the classroom anyway. So those little openings there are what we're looking down on here. Now, if the light just goes straight ahead, the light that arrives here is going to be what we call coherent. And this is actually at a line in space, but each of these two slits will experience the maxima and minima of these waves traveling along here at the same time. And so the light will leave these two slits in coherence or in phase. And so if you happen to travel the same distance away from these things, then the light would arrive in phase. Now, something that an approximation that we're going to make for these things is we'll imagine that there's some viewing screen that we can see these things on. And one thing is that the separation between these two slits, which we'll use a lowercase d for, this separation is going to be way less than the distance to the screen. For instance, you might have a screen that's 2 meters away from these slits, but these slits might actually be a fraction of a millimeter apart, or even a millimeter. The millimeter is only 1/1000th of a meter, so if you're 2 meters away, you're 2,000 times a millimeter if these are separated by a millimeter. So that's an approximation that we'll make. However, if the light from these two slits travels ahead in a straight line and hits the screen, well, actually what we'd have it do is kind of converge toward a point. But if this distance is 1,000 times as much as that little distance here happens to be, they'll be essentially parallel lines. And so there'll be a point in space where they arrive here in phase. And so we'd call that the central maximum, and it'll be a nice bright spot. But then there'll be other places where you get maxima, and let's consider how that can happen for these things. So I'll have my two slits here, and I'll draw a straight ahead line here. That's the one that you project it over to the screen, you get the central maximum. But then I'm going to imagine that the light goes up here at some angle, and these are separated by a distance d. Okay, this will be an angle theta. Well, if you play around with the angles here, this is theta. This will be 90 minus theta, but this will be a right triangle here. This will be theta again up here. And make sure you can convince yourself of that. Well, this amount here is the path length difference for these two things, and that's delta. Delta is going to be, well, D is the hypotenuse of that triangle. Delta divided by D will be the sine of theta. So delta is D sine theta. And what was our condition for constructive interference? When delta is equal to m lambda. So when D sine theta is equal to m lambda, we get maxima. And when D sine theta, which is delta, is equal to m plus 1/2 lambda, we get minima. Or destructive, a maxima is a bright fringe, a minima or a minimum is where you have complete cancellation happening between these things. I use the terms maxima and minima. I can't remember if they do in the book or not. I often have students ask me, what's a maxima? What's a minima? Well, they're plural, for one thing. A maximum is a place where the waves add constructively, then you get a nice bright spot. A minimum is a place where they cancel each other out and you get a dark spot. So those are the conditions for the maxima and minima. And it depends on separation between the two slits and then the angle at which you're viewing it. And I made the angle really big here, just because it's easier to draw the things. But this is where the path length difference shows up. And so you can end up deriving these things. Well, let's try some example problems for this stuff. We'll start off with a two-slit problem. A laser beam, 632.8 nanometers. Okay, that's the wavelength of the light. Is incident upon two slits that are 0.200 millimeters apart. Okay, that's really narrow, but that's typical for some of the things that we're going to look at. Isaac Newton tried to see wave effects for light and could never see it, but he didn't really have the means of, first of all, producing light on a single wavelength in a very good way. He could kind of do it by projecting sunlight through a prism and getting it to separate into colors, but it wasn't the greatest way to do things. And then to be able to produce something with only 0.2 of a millimeter apart, they didn't even have the metric system at the time of Newton. So he would have measured it in some other unit. Or I don't know, who knows what. But anyway, didn't quite have it. Oh, by the way, this particular wavelength is from a gas laser called a Hene laser or a helium neon laser. You have a gas tube that has a mixture of helium and neon. And at some point, I may talk about just how that happens to work, although it depends on some quantum mechanics and atom things that are beyond the scope of our class. But anyway, that's what we've got. So this is D. 0.200 millimeters is D. And the question is asking approximately how far apart will the bright interference lines be on a screen 0.500 meters from the double slits. So we're going a long ways. We're going to have our narrow slits here and separated by a distance d, which is very big in this case, 0.2 of a millimeter. And then over here, 5 meters away is where we're going to have the viewing done. This would be where theta is equal to 0. So that would be the central maximum. And we're going to get some other bright interference lines. By the way, this is another code word for maxima. So we'll have that. Well, let's work through the mathematics. We need to have d sine theta equaling m lambda. And for maxima, we have to have m equals 0, 1, 2, dot, dot, dot. Okay, we may be dealing with theta in radians here, but we'll see what happens. In fact, we can go sine theta is going to equal m times lambda divided by d, and we'll see how this works out. M, I'm just going to leave alone, 0, 1, 2, whatever. Lambda divided by d ends up being the crucial number here. So m times 632.8 nanometers, that's times 10 to the minus ninth meters. And dividing it by 0.200 times a milli is 10 to the minus third meters. And I'll get m times, whatever that turns out to be, which I haven't calculated yet. Shouldn't be too bad. Whoops. Nano is 10 to the minus ninth. Man, I screwed up both of my, forgot to put the minus signs on both my exponents. E minus 9, there we go. Okay, anyway, I get 3.16 times 10 to the minus third. And remember, m is 0, 1, 2, dot, dot, dot. So the central maximum is going to happen when m is equal to 0. And if you multiply anything by 0, you get 0. But I'll get these multiples of 3.16 times 10 to the minus third. Okay, here's something that we're going to be able to do. These are going to be small angles until, even if you get up to 100 for the value of m, you're going to have a value of the sine of theta that's going to be 3.16 times 10 to the minus 1, which is 0.316 radians. That's pretty small, but we're not going to go that far. We're interested in maybe the first 10 or 15 or maybe 20 of these maxima that we can see. And where are they going to show up? We'll use a small angle approximation for these things. And I didn't do a very good job drawing that. But anyway, Okay, so here's theta. So let's go ahead and figure out a little bit of math for this thing and see what it comes out as. The m=1 value. Remember how far this screen? 5.00 meters away. Is what that happens to be. Let's see. m=1. Where's that going to happen? Theta, or sine of theta, will equal, actually, if m is 1, it'll be 3.16 times 10 to the minus third is what its value is. If m is equal to 2, it'll equal twice that. Okay, so twice that is going to be 6.7, or yeah, 6.32 times 10 to the minus third. Okay, now let's figure out the value of theta in radians if that's the thing. And I need to take my calculator and put it into radians mode. So it's in radians, and I'll calculate the inverse sine, the angle for which the sine is 3.16 times 10 to the minus third. And I get theta is 3.16 times 10 to the minus third radians. Amazing. Okay. If I do the same thing for m=2, I'll get m is equal to, plug in the numbers, inverse sine of 6.32 times 10 to the minus 3. And I get, amazing, 6.32 times 10 to the minus 3. Well, let's let m equal 10 and see what we get here. So theta, in that case, remember, sine of theta is m times that stuff. So I'd get 3.16 times 10 to the minus 2. Whoops, no, that's the sine of theta. Theta itself, I'll just plug that in and see what I get. I get 3.16 times 10 to the minus 2. Actually, on all of these, it was 3.160, 3 or 6.320. On this one, I finally get 3.161, but I don't have that many significant figures. So even with an m value of 10, it ends up not making any difference between that. And also, if theta is equal to that, I'm going to calculate the tangent of that just for the heck of it. And so let's see, tangent of that answer. Okay, for that I get 3.162, but still tangent of 3.16 times 10 to the minus 2, that small an angle, is 3.16 times 10 to the minus 2. And here's the thing. For theta much less than 1, the sine of theta is equal to theta, as is the tangent of theta, approximately. Okay, it's certainly true to 3 significant figures out to this value here. And so we're going to be okay. Now, why I wanted to know the tangent of theta was because I want to know the distance to these fringes. And if I call this h over 5 meters is going to equal the tangent of theta. And these are the angles. So I can replace the tangent of theta with the sine of theta, and the sine of theta is equal to wherever it went. Oh, yeah. I can replace that with, let's see. Oh, we're after maxima. It's just going to be, oh, where was that? Here it is. The sine of theta was equal to m times 3.16 times 10 to the minus third. So is the tangent of theta. So it'll be m times 3.16 times 10 to the minus third. Okay, this is kind of complicated, but I'll end up with h, the distance that's away from there, is going to be m times 5.00 meters. Oh, this is m is that 0, 1, or 2 thing. This is a meter times 3.16 times 10 to the minus third. Well, I can do this multiplication in my head, and I'm going to group the 10 to the minus third and the m together because I'll get this lowercase m. Remember, that's the 0, 1, or 2. 5 times 3.16 is, let's see, 15.80. And then what I still have here is 10 to the minus third and meters. Well, 10 to the minus third is a millimeter. So that'll be 15.8 millimeters. And the distance between the bright fringes is going to be the first bright fringe, actually the 0th will be at 0. The first bright fringe is 15.8 millimeters away from that. The second will be another 15.8 millimeters away. And eventually you'll get up to the 10th one. It'll be 150.8 millimeters away, which, let's see, that's still only 15 centimeters or 15.8 centimeters. So here we are at 15.8 millimeters, and you'd have 10 bright fringes, actually 11 if you count the 0th one. You'd have 11 bright fringes between my fingers here on this screen that's 5 meters away. So, and they're going to be evenly spaced going vertical as you do that. So that's kind of an interesting problem. Okay, gonna flip this. Where was my second problem? Oh, there it is. Okay, this is a different sort of problem, and I'm going to show you a technique for drawing these things and for figuring out the resultant of these waves that's going to be useful for figuring out the intensity of the pattern as a function of what the phase difference happens to be. And that phase difference arises because of a path length difference because of going in different directions. So let's figure out how to add these two things together. And remember, I mentioned that the intensity of an electromagnetic wave is proportional to the square of the electric field. So by adding these two things together, I'll find out the total electric field at some point in space. We don't have units on here. Electric fields have units of newtons per coulomb, or let's see, volts per meter is another way of expressing it. But at any rate, we're not worried about that at this point. We're just going to pretend we add these two things together. So what I'll do to figure that out is to draw two vectors in space. And this is called a phasor diagram is what I'm going to draw. And one of these, oh, they're actually at right angles to each other. Well, that may be nice. Here's E1. This could represent E1 here, which has a magnitude of 6 and stretches out there. And then we'll have a vector E2 that's going up here. This is E2, and it's got a magnitude of 8. And on this thing, I'm going to label this angle here as 100 pi times t. And then this angle is also 100 pi times t because it's just a continuation. But this angle here is going to be 100 pi times t plus pi over 2. Pi over 2 is a 90-degree angle. So that's what I happen to have here. Now, I know this is really bizarre, but if I project back on this thing over here, okay, this is the side opposite that 100 pi t. Okay, that E1. This will be the sine of, actually, it'll be 6 times the sine of 100 times pi times t, because the hypotenuse has a magnitude of 6. Well, that's the projection over here on the vertical axis. So this will be 6 sine of 100 pi t, and I kind of ran it down there. Well, let's see, what about this one? I'd have to do a little bit of work. This will be 180 minus that 100 pi t plus 2, and a little bit different, but it ends up being the projection on the vertical axis is also the sine thing on that one, because sine waves are symmetric about 90 degrees is the thing. So this will end up equaling 8 sine of 100 pi t plus pi over 2. Okay, that'll be this thing here. Well, the length of these two things will end up being, actually, you don't need rocket science to do this one because they're 90 degrees, or this is a 90-degree angle. It'll be the square of this one plus the square of that one will be the resultant wave. But as far as its phase is concerned, that's a little bit harder to figure out. That's going to be this thing here, and have to do a little bit of work to figure that out. But turns out this is 6, 8, 10 when you've got a right triangle like that. And that'll be the magnitude of that resultant wave. But what about its phase in there? What is that going to look like? Well, as time goes by, this 100 pi t will increase, but so does this thing. This 100 pi t plus pi over 2 increases by the same amount. And as time goes by, these two arrows, this vector and this arrow, will rotate around each other here, always staying at a right angle with respect to each other. And so that's kind of neat. They'll maintain a constant phase with respect to each other. That makes them coherent waves. And so that's something that comes out of some of this study. Trying to remember. Yeah, we do need to figure out the intensity of this. So I need to go a little bit farther into some abstract math here, and you might be resistant to this, but you'll live through it, believe me. Oh, let's see. Okay, a nice clean piece of paper on one side at least. Yeah. Yeah, there won't be any calculation math in here, but there is going to be some math. So this is something that is done for, it's abstract, these phasor diagrams, but it's a way of figuring out the intensity patterns for various things. And we'll use this math for, well, we're going to use it for 2 slits and 3 slits. Actually, some of it anyway. For 2 slits and 3 slits, we're just going to be interested in the places where you can have maxima and minima. But whoops, need a ruler again. I'm going to imagine, and I'll make these things the same length. And I'm using inches on here, but that doesn't matter. It's just a length. So here's my first one. And this angle here is going to be omega t. And then I'll add to that a second vector, which has same magnitude. At least I hope. Yeah, it does. And actually, okay, so this was omega t. If I sketch this, this would also be omega t. But this is going to be the phase difference between these two vectors or two electric fields that I've got. And one of them at this instant in time, I can write as just, I'll call it E1, I guess. Actually, this is the one I'm going to call E1. This will be E2 down here. And it doesn't matter what order I happen to write those things in. But this will be the phase difference between the two waves. So this is, and this arose or could arise because of a path length difference. So E1 is going to equal whatever its amplitude happens to be times the sine of omega t plus phi. And E2 is going to be this vector down here. It's just going to be E sine of omega t. So that's the way that I'm describing these things. Well, let's see. This angle here is actually 180 minus phi. So write that in here. And I would like to know, this is the resultant here. And I could think of it as either the product. I think your book refers to it as E sub p or something like that, where it's the product of these two things. So let's go ahead and just write that onto there. But guess how I can figure that out? I know this side, I know this side, and presumably I know the angle between those two things. That's the law of cosines. And so law of cosines is this. This opposite side here is going to equal this one squared plus this one squared, but it turns out those are both just e's. So the lengths of these. So it'll be e squared plus e squared minus 2 times the length of this times the length of that, which is e times e again, times the cosine of 180 minus phi. Whoops, ran out of paper. All right, well, I can shorten this a bit. It'll be e sub p squared is going to equal 2e squared minus 2e squared cosine of, cosine of 180 minus phi. Well, that looks like 2e squared out front to me, I think. Oh, by the way, the cosine of 180 minus phi, we can figure out that. That's a little big thing. The cosine does this. Something like this. And comes back up. So if you've got some angle phi, the cosine of 180 minus phi ends up being the negative of that. So cosine of 180 minus phi is the negative of the cosine of phi. So this thing ends up being 2e squared plus, plus 2e squared cosine of phi. So that's one thing, which ends up being 2e squared times 1 plus the cosine of phi. So there's all kinds of weird math going on with these things. But there's a trig identity that 1 plus the cosine of phi is equal to 2 times the cosine squared of phi divided by 2. Holy cow. So what we get for this product here is that, let's see, 1 plus the cosine of squared, that e sub p squared ends up equaling, let's see, we get another 2 out of there. It's 4e squared cosine squared of phi over 2. And if we're just interested in e sub p, we take a square root of everything, and it'll be 2e, and then the absolute value of the cosine of phi over 2. Huh. Well, that's kind of interesting. Now, something that shows up is that the intensity ends up being the square of this thing again. And so we get a bunch of other weird stuff, but the intensity of the light is proportional to the square of that product, with a bunch of stuff tagged onto it, like 1/2 epsilon naught c stuck onto that. But if I take the value of this when phi is equal to 0, that would be phi is 0 at the central maximum. So at the central maximum, the intensity is going to be, let's see, actually it'll end up looking something like this. 2 epsilon naught c e squared. But I can write the whole thing for the intensity in terms of that. And here's what the intensity is as a function of phase difference. And it's this result that's going to be important. I naught cosine squared of phi over 2. And this is the important relationship for the intensity of a two-slit pattern, and it's in terms of the intensity of the bright central max. And so at other places, you'll end up with other intensities. However, if phi has a value that will make the cosine of phi over 2 equal to 1, then you get something that's just as bright again. And so let's see, if phi is equal to, let's see, when is the cosine equal to 1? It's equal to that at pi. It's equal to that at 2 pi. So if phi is equal to pi, whoops, except we're dividing by 2. Yeah, we have to worry about the multiples of that. So anyway, if pi is equal to 2 pi, then 2 pi over 2 is pi, it'll work, or 4 pi, or whatever, is when we get the bright intensity things. And the next problem, this will probably be the last one that we get to today, if I can remember where it is. Yeah, coherent light from a helium neon laser, again, is incident on two parallel slits. By the way, these lasers are used for a lot of examples because we've got a couple of them in the lab, but they produce a nice, stable, bright line, and it's always that particular value. A lot of the inexpensive lasers you get, like the handheld little ones that are red, aren't so precise in their wavelengths necessarily. So just because of the way they're manufactured. Anyway, two parallels, same distance apart, but what's the distance to the first maximum and its intensity relative to the central maximum on a screen 2 meters beyond the slits? Well, we're going to do something a lot like I did last time. A lot of times I draw my two slits kind of looking like this, but um, okay, so I'm doing this every time to stress this. This is an angle theta. This is the distance d between the slits. Okay, and in this case, d is 0.200 millimeters again. But here's the path length difference, d sine theta. And for maxima, I get that d sine theta is equal to an integral number of wavelengths. And we're interested in the distance between the first maximum and its intensity on a screen 2 millimeters beyond the slit. So somewhere over here, we'll have a screen and we'll have the central maximum. And then we're interested how far up is this first maximum after that. So I'd like to know what that is. Well, it's going to happen when d sine theta is equal to 1 times lambda. The central maximum is 0 times lambda. So I want to know d sine theta is equal to lambda. Okay, well, sine theta is going to equal lambda divided by d, and I think that's the same lambda and the same d that I had before. So it'll be 632.8 times 10 to the minus ninth meters divided by, this is actually 2.00 times 10 to the minus fourth. So I'll do that. And that's meters. The meters divide out. Do I get a small angle on here? You bet. 632.8 divided by 2 is going to be 316.4. I had that last time. Or to three significant figures, 3.16. Let's see. I'll get it. That'll drop that. Times 10 to the minus third, I think. That should be the same thing that I had on that other problem, wherever I put it. Or you can do that in your calculator. Check that out to be positive. Let's see, that'd be 10 to the minus fifth. Yeah, I pick up that. So that's the value of the sine theta. Is that a small angle? You bet. And so when I figure out this height here, looking like that, it'll be h over the 2.00 meters. This one's only 2 meters away, not 5, but h over 2.00 meters is going to equal the tangent of theta, but that's about equal to the sine of theta, which is equal to this, and it's equal to theta itself. So that distance from the central maximum up to here is just going to equal 2 meters times 2.00 meters times 3.16 times 10 to the minus 3. That looks like 6.32 about. And actually, if I'd kept all my significant figures, it'd be 6.33, but close enough anyway. 6.32, that's where the uncertainty lies, times 10 to the minus third meters for 6.32 millimeters. Okay, what about the intensity of it compared to the central maximum? This will be the last thing we'll have time for today, but the intensity is going to equal I naught times the cosine squared of phi over 2. Well, what's the phase difference here at that particular thing? If I've got that the path length difference is d sine theta over lambda times 2 pi is what phi happens to equal. And in this case, let's see, d sine theta over lambda, actually sine theta is that, but oh, d sine theta was just equal to lambda. So this is just going to be 1. This part is just 1 on this thing. So I'm going to have that phi is equal to 2 pi. Well, 2 pi divided by 2 is pi. What is the cosine of pi? Come back to my drawing here. Here's pi. Here is 2 pi. Well, the cosine of pi is -1, but I want the cosine squared of pi. So it's going to be 1. And that's just 1 in this case. So the intensity is the same as the central maximum at that point. Now, it turns out there's another effect that goes on that we won't learn about until we get to diffraction. And they won't stay 1 forever, but usually the first one out will be just as bright or nearly as bright as the central maximum. But we'll learn more about that later. It's an effect called diffraction. Okay, there was a lot of stuff in here, but a really important thing is to realize the path length difference, d sine theta, is equal to m times lambda, and that's where you get the maxima. By the way, there's a formula in your book that I don't think they give enough emphasis to, and this is the formula. It's on, well, it's equation 3513 in my book, but it's this, that the phase difference is 2 pi d over lambda. Now, d over lambda is the, or actually, yeah, well, oh, it's got a sine theta on here. Okay, if I group this, d sine theta is the path length difference. Divide that by lambda, and you get the number of wavelengths that fit in that path length difference. Multiply it by 2 pi, and you get the phase difference. And that's maybe the most important formula in this chapter, is that thing, and getting the hang of where that comes from. So anyway, that's enough for today. And 7 o'clock tonight, we'll have the question and answer session for, I think, both the laboratory and the homework on geometric optics. So we'll be able to deal with all that stuff there.